Yes, nice. Okay. Guys, we're gonna get started for today. We're gonna. Oh yeah, give me a mic. Yeah, I think Kwai has a day with me, so you can't make it today. So I originally gonna start with a Kahoot to kind of refresh everyone's coding knowledge, but then everyone who's here basically are pretty experienced in coding. Do you guys know if anyone who's not here are they coming or are they just not coming anymore? Did we scare them off with the coding and the? Tom's coming. Okay, cool. Okay, we'll just run through this. So people who are the experts at Python, try to be as quick as possible and get the highest score. There's a prize for the winner. Okay, but then and then people who maybe need a refresher with Python, this is a good learning opportunity. The music. I'm not sure. Okay, I'll broadcast its kind to. Okay, it is loud enough. Best we can do. Alright, everyone here? Alright, let's get started. Alright, be quick then. So, for this case, every single time we run it, it will be, if I is equal to 3, as soon as it hits that, it will break. Basically, the break means get out of the loop. So see how this happens before the print I? Yeah, it's a bit long, isn't it? We might not. So this is from the ITP workshop. It's a bit long. Okay, we'll see how much we can get through in 20 minutes. Okay, so this one is the same thing, but when count gets to 5, it wouldn't actually execute again, right? Because it has to be less than or equal to less than 5 for it to enter this while loop. So what is it? How many times will the while loop execute? Yeah. So even though I guess where people are coming from, but then it prints at 0 at the start, right? The first count when it enters the while loop is equal to 0. No tricks here. So for this one, remember how range, it starts from 0 and then it's not inclusive of 3. Who's going well? Lewis? Guys, he hasn't done coding before like the week before. Come on, you can't lose to Lewis. So, okay. So capital case matters, okay? Who said error? Okay, but this is perfectly fine. Print can take numbers as inputs as well. So this will end up being a number, which is 38, as most people quickly calculated. So it first tries if it's greater than 80. It's not. Is it greater than or equal to 70? It is, so go merit. Fail. Lewis still up there. CJ, Nathan, Kev. Nice. Yeah, guys, come on. It's got a quotation mark. We're looking at quotation mark, okay? That's a string. Oh my god, guy. Lewis. Okay, awesome. Oh, it's not just this carousel, but I can see why you chose it. So it ignores the whole line. It's really good good practice to comment your code. Very nice. Oh, wait. Did someone want? Okay, I think someone clicked on it. Okay, misclick. Okay. Okay, 5 seconds for this one. 3, 2, 1. Oh, nice. I think Lewis is still on top. Use it for the age. So there's no quotation marks here. It doesn't work. If there's no quotation marks, Python will think how they're all variables. So I think we're getting some harder questions now. So I've got more time for this one. Okay, so we got quite a big spread of answers there. But what's the first thing that's going to be printed when I go to, let's play computer. So we have for I in range 3. What is I right now?
0.
Yeah, it's 0. So it will print 0 to the terminal, and then it goes into this block. For J in range 2, what's J right now?
0.
Yeah, exactly. So it will be 0, 0, and then what's the next line that will execute?
WJ.
Yeah, because we're not exiting out this loop, right? We have to go through this loop twice before we can get out of it. So that'll be 1. And then after we do this twice, we go back to here. And then what is I now? Yeah, really good. So this is a nested for loop, and this is really important when dealing with matrices because matrices are basically just a a list in 2 dimensions. So that's the answer. See if that changes things a bit. Okay, CJ back on top. I think this is a loop question. Okay, so let's have a look at this one. What is I? And so if first for I in range 3, for j in range 2. So basically I and j are both starting out as 0. So print 0, 0. And then what's the next line that will be printed after we print out the 0, 0? Yeah, because we'll go back to here, right? I is still 0 because we're still kind of within this j block. But then j will be becoming 1 now. And then that means that we'll have executed the first time this block goes. So we go back to the very start, and I is now 1. So it'll be 0, 0, 0, 1, and then 1, j will be 0, because this block executes again for the first time, right? Okay. Who's D? Nothing? Nice. Okay. One more second. Yeah, nice. Basically 3 times 2. Quick math. Okay. So it completely gets out of the for loop or while loop as soon as it hits that block. Okay. So this was something from yesterday about how Python does the parentheses. I think the question from yesterday, the calc was a bit unfair because no one ever writes like a huge statement like that. You always wrap in parentheses. So for example, the or executes if either of the statements next to it are true. So in this case, statement 1 is this, statement 2 is this. So is statement 1 correct? Is this correct? No, it's not, right? Because it says A is not equal to A, which is wrong. So this part is false. So now we need to look at the right-hand side of the or statement to see if it executes. So is 2 greater than or equal to 3? It's not, but then there's a not, so it flips that. So this overall thing is true. And because an or statement is like if either of them are true, it will execute. Whereas an and statement requires both sides to be true. So always, Python does weird things with the with the wrapping. Like if you don't put parentheses on, so make sure to parenthesize it very nicely. Makes it more readable as well. Some very quick questions, 5 seconds. Nice. Another quick one. Huh? So this is how this is different to arrays. Arrays can only store numbers, right? But lists can store anything, so that's false. So remember how Python is zero indexed? So the third element is actually the second index. So the first will be 0, and then 1, and then 2. Nice. Yeah, so -4 all the way to the end. So -1, -2, -3, -4. So it'll be 2, 3, 4, 5. So why do people choose 1, 2? Just out of curiosity. Oh, okay. Yeah, so -4 just yeah, be careful the side of the column it's on, right? So if it's like column to -4, that means that it will be it actually just be 1. So be careful about the location of the colon. Lewis rising back up. So this is a very valid way. Do people not read the not? There's an R there for some reason. Alright, my bad. But yeah, you can do dot reverse. This is a method. So, okay, going. Lucky. Did not see the exclamation mark. But yeah, good job catching out on the space. So that space is character as well. Last couple. So this is revising the references stuff. Yeah, so most people got that well done. Basically, for this one, a list or dictionary, it does get modified by a function. So you can see that the original dictionary, which is original key to original value, and when you pass this dictionary into the modify function, what this does is that it adds a new key value pair, right? So it has a new key and new value. And because you pass it directly into the dictionary, it will change it. So when you print it back out, it will have the original key and the new key. So this one is wrong because it doesn't affect the original key. You're not getting rid of the original key. And this was incorrect as well because dictionaries are passed in by reference, not by value. Smiley face on the rise. Really nice. So what's happening here is that you start with x equals to 5, and then when you run the function, remember how this x is different to the x on the outside, right? Because this is a variable. This is not a list or dictionary. So when you print this out, it will print 10 first, and then it will print the 5, which is not modified by the function. Okay. So if you want to make a variable outside the function, you can use a global keyword, but that's generally not good practice because you want to keep the functions and the overall code as separate as possible. Okay, last question. Nice. So basically, this is a demonstration of what a global character does. So basically, it just tells the function to look outside of its own bound. So right now, this function doesn't have any variables inside it, right? So when you say global x, it's looking outside the global code to find a variable called x. It found it called x equals to 10, and then it can modify it to be equal to 20. So that means that the code that we printed will be 20. Okay. Well done. Nice. So that's it. Tomorrow will be a lot less serious so beyond the IPP level. So if you guys haven't done the Kaggle course, I think it's rated for, is it 5 hours? It's really important to do that before tomorrow, otherwise tomorrow's content will be quite a bit more challenging if you haven't seen it before. Okay. So we'll finish the last of the linear algebra slides now. Since we have a bit closer now, what are the main questions that you guys want to go through from yesterday? Like, what is the part that's most confusing? Do you guys want to get a mic around, or just it's closer now? Anything that anyone wants to go through specifically? So the main things was matrix multiplication that we saw in the feedback. This is probably the most important part. It's kind of what everything's been building up to. I'll share this screen again, But for matrix multiplication, there's just three things that's really important. The first is understanding dimensionality to see if things can multiply together even. So can this one multiply together? The word embedding matrix as well as the embedding of another word called lion. Yeah, good, because there's 4 rows and 7, so 4 rows, 4 by 7 for the first matrix and 7 by 1 for the second one. So basically what happens is just a dot product, right, of to the first, so it'll be a 4 by 1 matrix and each of them storing the dot product. So hopefully this matrix multiplication can make sense in terms of why we care about it in the first place, which is just a really convenient way to calculate a lot of dot products together. And this is how, you know, the parameters from earlier of how there's like 16 billion parameters. Matrix multiplication is really the only way, so with addition, how these parameters change and learn over time. Okay, so we're going to finish off linear algebra with just a quick run through of the different types of matrices. So the first one is transpose. It's something very important in code because remember I said it's so important that the matrices have to be the correct dimensionality, the compatible, yeah. Oh yeah, we are. Yeah, good question. Okay. So basically, a lot of the time when you code, like the things wouldn't be in the correct dimension, so you need to use a transpose matrix. So what a transpose matrix does is that it converts, so it's called a hat T, and what it does is that it converts a matrix and basically flips it on the side. So see how this matrix, the rows are 1, 2, and 3. The second row is 4, 5, 6. So basically the rows become the columns. So the first row of the original matrix, 1, 2, 3, becomes the first column of the modified matrix, right? 1, 2, 3 goes down here, and then 4, 5, 6 goes down there. So basically it's a kind of rotation. So if it starts as a 2 by 3 matrix, it's going to end up as a 3 by 2 matrix. So the reason we do this is because we need to make sure that dimensions match during matrix multiplications. For example, in this case, we can't do an AB, right? Because this is a 4 by 1, and this is a, 4 by 7, and this is a 1 by 7. And this is how most of your code will be, because for example, your word embeddings will be stored as a vector like this. So you can't actually multiply together. So if you want to figure out the relationship between this embedding matrix, as well as how each of these words relate to, say, the new word, you're going to have to make the transpose. So it's very simple in NumPy. It's just a dot T. As long as the first thing's a matrix, you can just do a dot T, and then that will allow it to be a 7 by 1 vertical, vertical kind of vector, and the matrix multiplication will work. Just like that. Okay, so other matrix types is less important. A square matrix, so it's just a matrix that happens to be a square. The same number of rows and the same number of columns. This is a diagonal matrix, so all the non-diagonal elements are 0. So basically the main diagonal is going all the way from the top left-hand corner all the way to the bottom right-hand corner. And because it says everything else has to be 0, this has to be a square matrix, right? Because you can imagine that only a square matrix has a diagonal that goes all the way from the top left to the bottom right. And don't get too hung up on the definition of these. The main goal is to, next time you see it when reading some like blog or something, just know what they're referring to. This is identity matrix. This is quite important because it's the same as diagonal matrix, except that all the elements are 1. So basically, you can see that all the other elements are 0, and then the main diagonal is 1. And the reason this is important is because this is kind of what generalizes the concept of 1 in the matrix world. Because this has a property that when you multiply a matrix by I, which is the identity matrix, it will return the same matrix back. So for example, in this case, this is just kind of more math kind of format to be aware of. But A times essentially 1 is the same as A, right? So it's like any number multiplied by 1 is still equal to itself. And all the identity matrix does is that it generalizes this concept to all matrices. And this symbol is like an upside down A. It means for all. So what it's trying to say is that for any possible matrix A, right? That's what, so it's kind of defining the bounds of A, what A can be. This formula will always hold. So for no matter what type of matrix A is, if you multiply I to it, it will still be equal to itself. And this leads us to the concept of what the inverse matrix is. So remember how I generalizes the concept of what 1 is in the matrix terms. What inverse is generalizes the concept of division. So remember how a fraction, like you can't really divide by a fraction, right? What you do is that you multiply by the negative reciprocal. So you can imagine the inverse matrix as simply the negative reciprocal, kind of the same analogy to what it is to a fraction. So when you multiply, any number by the, not negative reciprocal, just a reciprocal, if you multiply any number by its reciprocal, you're going to get 1. And it doesn't matter the order of that, right? So it's the same as what the inverse matrix is. If you multiply a matrix by its inverse, you're going to get I, the identity matrix, back. And feel free to test this out, by the way. So, for example, if you were to do a matrix multiplication of A and A inverse, let's have a go at this. So what's the dimension of A times A inverse? Yeah, 2 by 2, because this is 2, 2 times 2, 2, right? So only square matrices can have inverses. And next thing is, what A will be a, so the new matrix will be kind of a 2 by 2 matrix, right? So what's the first row and first column? Where do we grab that from? Which dot product is that? Yeah, so it will be grabbing the first row from the first matrix and the first column of the second matrix, right? So 4 times 6 will be 24, and then 7 times negative 2 will be negative 14. So that'll be 24 minus 14, that'll be 10. And then 10 will be multiplied by the scalar, so it will be 1, right? So that's what we expect, because the identity matrix has the first entry is 1. Okay, and how you do this in NumPy world is that you go to NumPy, the linear algebra module, and you select the inverse. You just dot inverse A. That's how you return the inverse of A. And it's so much work computationally, by the way. Like if you ever try to go to math textbook or even search up how to calculate the inverse, it's like to do this, it's just basically, so this is a really easy one for 2 by 2 matrix, but for 3 by 3, 4 by 4, it gets exponentially more difficult. So we're not going to go through that at all, but yeah, for our perspective, it's just really nice how we can get NumPy to do all the work for us. So this is a really nice matrix, because do you remember how I said it's so difficult to compute the inverse? Notice anything special about this format? The transpose of a matrix times a matrix is equal to the matrix times the transverse, which is equal to I. So what form does that look really familiar to? Yeah, the inverse form, right? It's actually the exact same form. So by definition, an inverse matrix is a matrix that when you multiply to the original matrix, it will form 1, right? So can you see how this form is basically the same as the A transpose form as for orthogonal matrix? So this is really, really good, because normally it will be really hard, even for NumPy under the hood, to compute the inverse matrix. But if a matrix has a special property that is orthogonal, that means that to calculate the inverse is trivial, right? So rather than having to do the difficult computation, let's say that A is an orthogonal matrix. So that means that the A inverse would just be 4, 7 going down, and then the second column down will be 2, 6, right? So this is just an easier way to calculate the inverse matrix. So yeah, this is a very convenient thing, and you'll see in a lot of formulas, we try to make orthogonal matrices just so that it makes life really easy computationally. So this is, it's very tedious normally. Okay, so the cool part is about applications. So the most important application is that all the large language models are doing, and any deep learning model, is just all different matrices multiplying together to give you the output. But in terms of another thing that we're really important for is PCA, which is dimensionality reduction. So do you remember how for this graph, right? Now, cat, each word has 7 different dimensions. So it's obviously impossible to visualize a 7-dimensional graph to see where every word is in space. Does that kind of make sense? So for a 3-dimensional graph, you might be able to plot, like one axis might be living being, one axis might be feline, and one axis might be human. But for a 7-dimensional graph, a 7-dimensional word, it's obviously impossible to visualize. So how do we know what our code is actually doing and if the relationships it's capturing is actually making sense? That's basically through PCA. So there's a lot more application of this, by the way. So do you guys know Zach Starr? He's like a comedian YouTuber, but he makes a really good, this is a really nice video on the importance of matrices, and you can see that like in any world, from economics to science to computer science, and especially deep learning, it's basically what's powering all that. But the thing that we're exploring today is how to use it as a dimensionality reduction technique. So basically, it helps us to visualize things by projecting to 2D. So you can imagine that it's 7-dimensional. It's impossible to visualize, but it's almost like we're compressing it to 2 dimensions. And how we do that is we basically select 2 dimensions. That's the most important. So just a component of how cool it is. So this is a photo, right? And originally it's 3,000 pixels across, tall, and then 4,000 pixels across. So this is a very, very large. So you can imagine like this is in the millions, right, in terms of how many data points are actually on here. But this is what happens after you do PCA. So this is actually just with 10 components. So going from like millions to just 10 components. And it's not the best, obviously, but it's still recognizable. It's 2 cats on the bed, right? 25, it gets a bit better. 50, it gets even better. 100, it gets even better. 150, and then at 250, it's almost, it's very hard to distinguish from the original, and that's coming from 7 million originally. So what powers this is that we're going to start with a 2D example. We want to retain as much information as possible, but only using 1 dimension. So how might we do that for this example? If we only have 1 line rather than the x-axis and the y-axis, what we want to do is that we want to create an axis that can capture most of the relationships on this data set. Any idea where we might draw that new axis? Yeah, so it's kind of like a line best fit, really. So if we were to draw a new axis there, let's see what we have, right? So let's say that rather than defining this data set by 2 variables, an x value and a y value. So for example, this point will be, like 0.2 on the x and then 0.3 on the y. What we're going to be defining this is we're going to be defining this as a new number line. So you can imagine that, for example, a new number line, this might be the 0. And then on a new number line, this point might just be represented by -5. And this point might be represented by 5. This point might be represented by a 1. So what we can do to retain as much information as possible is that we just go along where most of the data is. So how much information are we missing out by representing a data from 2 dimensions to 1 dimension? So what is something that we're inaccurate about? As in, where is the loss? Yeah, perfect. It's the distance away from the line, right? Because we can only imagine the horizontal value of the point. But what we're missing is that we're essentially treating, so imagine that, for example, these 2 points are kind of on the opposite side of the line, right? By our dimensionality reduction, we're basically treating both of these at the same point because they both kind of fall onto our line like this. So that means that we're unable to distinguish at this point, for example, is a bit lower on the y side, and then this point is a bit higher on the y side. So all this is information that we're losing. Now, this is quite a nice data set in that it's unrealistic, right? Everything is very well along the line. And you can imagine that for something like a cat, all of this is basically anything from 0 to 1, right? All these pixels. So it's a lot harder to capture it simply, but it really does remarkably well. So this is twofold importance. The first, and probably most important from our perspective, is that we're able to visualize what our 10,000 dimension word embeddings look like in terms of their relations to each other. But also it can make some data sets easier. So I think I got some example here. The hard, oh yeah, okay. But remember the hard data set, for example, like we can visualize that, all that as well. So what we do is that we essentially rotate the axis a bit, and we put the line through, and we just essentially drop the values down. So essentially, can you see how our new coordinate plane is the x dash? Basically, this can be at 0, and then the new values will be only represented by the horizontal, right? And the y value is just the things that gets dropped. But you can see that we capture so much information already just using the x value. So the only thing that we're missing will be the vertical distance. And remember, the rotation of this is the linear transformation. Has anyone watched the 3 brown 1 blue videos by any chance? Yeah, if you have, it's bloody awesome, right? It's just the first 3 chapters, and it's really entertaining, I think. Okay. Through this method, we're basically halving the size of data and basically retaining all the information. So it's a really nice way to go from 2D, for example. Can you see how if we draw the line along here and then drop, that's what our data will look like. And also we can go from 3D to 2D. So this is a bit hard to visualize, but essentially, if we go to 1 dimension, right, that means that we're just basically projecting everything in space kind of all to the closest point on that line. But then 2 dimensions will be like, okay, what we're seeing is that if we were to project everything on 1 dimension, can you see how there's a lot of loss that we're doing with the vertical distance? And by having a 2nd dimension, what we're able to do is that we can account for some more of that. Is it perfect? No, because it's just imagine that it's a 3D set dots that I just squish onto 1 flat plane, and then you can squish again to make it 1 dimensional, right? But it's it's quite cool to see how much we can capture just by using this algorithm. And you can see that this is how these graphs came about, right? But the problem is, see how before we might have an idea of what each embedding dimension is. For example, we can imagine that this is living being, this is feline, this is human. But we're being even more abstract now by completely losing sense of what we are. So we have no idea what it is along this axis, and we have no idea what is along this axis. So again, on one hand, it does contribute to the problem of AI being like a black box. We don't know what's going on. We just can see that, oh wow, it captures relationships really well. And this is a real example that once you compress these down, this will actually happen. And this is just by manually labeling data. So getting really close. And this is even cooler. It's about the relationship words. And kind of another demonstration of the application of this is that if we know the relationship between king and queen, right? We know that, for example, in this space, to go from a king to a queen, we move, say, 1 right and 2 up. So that means that going from men to women, we can also go 1 right and then 2 up. So for example, if we have a word like, what's another male term, like policeman, you might be able to, if you know where policeman is, you might be able to go to 1 right and 2 up to find policewoman, for example. And all that is powered by vector addition.
Just a question.
Yeah.
So you mentioned when you 70 to 2D, like the top row.
Yeah, so this one?
Like you said, we don't actually know what the exact relationship is. It's sort of like things are similar together. But intrinsically, aren't you combining all the information from all of the categories onto the axis?
Yeah, it is. So what I mean by that is I can't explain what's going on at the right side, but you can visualize it like this. So for example, this is, let's say on this side is how much something is an animal and how much something is inanimate. And inanimate is basically capturing both, okay, is it human, is it feline, is it living being? Kind of like one category that captures 3 dimensions. That kind of makes sense, right? So that's why it still retains the relationships. We just can't explain it. As in, we just don't know what this axis is and what this axis is. For example, this axis could be size for all we know, and maybe that captures verb and plural and stuff. Does that kind of answer your yeah?
Is it mainly used as for like a human to look at it?
Yeah, it is. It's used all the time to visualize what our data is doing because, it's like a really quick way to fact check how you do rather than running it on, for example, a testing set. You can just have a look to see, oh yeah, it looks about right, and you can see relations. And this is really important because I'm not sure if Quaslight had this earlier, but when transformers model, so what transformers models and why it's so important is because it can modify the embedding of a word depending the context it's in, right? So for example, in this case, if dog is used as like an animal, well, it'll be really close to cat and kitten. But if the dog is in the sentence, I don't know, like he dogged the boys, it will be like in a completely different position in space. It will be a lot similar to other words. And this is basically, it's just a way to visualize what our model is doing and kind of intuitively check that it is doing the right track. It is trying to basically do what a human is trying to do. Yeah.
And I'm just curious that for the 3D to 2D, is it like they find like a best fit plan among all the points, or they somehow find a way to fit in all the points in, or they just take the points that are at the best fit plan?
So how it's actually done is this is what is eigenvectors and eigenvalues, which is something I'm not even going to really cover because that has to do with a lot of linear transformations. So intuitively, it's enough to think of it as just dropping to the. So if it's, for example, a 3D to one line, it's just basically all the points zooming into the closest point of the line.
So all the points are still
It's just like flattening it onto the.
It's just flattening, exactly. Yeah.
It's like collapsing into the low dimension.
Yeah, it is. But in terms of how the math is very clever, but very, very complicated. We have a PDF of like how it works deep down if you guys want to dive into it. Again, the thing is for what we're working with these days, it's not that much helpful for learning to like understand the algorithm. It's like literally 3 pages of working out, by the way. Like this is but then it's just important to understand like how this comes about and the intuitive understanding of that still maintains some relationships, right? Okay. So this is a real example actually. So one of the assignments was like a word embedding thing. So basically we use PCA, we had a data set we're trained on, and then we kind of compress it down to 2 dimensions. And I put in some extra words to just see how it end up. And this is really cool because you can see physician and surgeon, kind of doctors, people, right? They end up on this own bubble here. These are all the organs like heart, knee, brain, elbow, stomach, lung. So I was maybe expecting heart and lung to go closer. I don't know, but lung and stomach, maybe it's using more context together. You can see bone used all the way over there. So it shows that ortho is so far away from everything else in medicine. But mainly, I think bone is used in a lot of different contexts comparing to heart and lung and knee, which is more maybe medical, whereas bone can just be used a lot more daily life. So that's it for the linear algebra section. Anyone have any questions on the go through for linear algebra before we keep going? Okay, so if you guys want to explore more, the 3 brown 1 blue is a really nice to provide the math intuition of what's going on. What we've done is completely from the computer science perspective of thinking of vectors and matrices. It's just a way to store numbers really efficiently, and a really efficient way we can modify them with matrix multiplications. Yeah.
So a question, like let me know if it's out of scope, but like how do you pick which features, like in a word embedding?
Yeah.
I think we were having a conversation yesterday. It's like how do you actually figure out what features and what values they have? And then also in the dimensional reduction thing, like how do you figure out which dimensions you compare to collapse down?
Yeah, so okay, this is a bit beyond the course, but beyond right now. But what we do is that we actually go along the direction with the most variance.
Okay.
So see how this dimension doesn't have much variance because they're really tightly together, whereas this direction is so spread apart. So that is how we choose a dimension. That's the first one, right? So we go from 2D to 1D. The direction that we want to go in, visually is basically line best fit.
You want to capture the most variance.
Yeah, exactly. So the most variance. If we were to capture the widest, we then just want to capture the widest distribution of points, right? So from this point to this point, like this direction, we had the most variance. And what the points are is like it explains the variance. So for example, this point will be like, two that way and then two that way. So it's just the algorithm trying to think, okay, there must be something along this direction that we want to capture. And what's the other question?
From a word embeddings perspective,
Yeah.
like how do you what selects the features, and where does that come from?
Yeah, really good question. So that's the magic of machine learning, right? We cannot possibly like annotate all these words, and that's something they did before, like way earlier start. Because just think about how hard as a job it is to turn languages into numbers, right? Which is what computers need to work with. So that's the thing. So on a very superficial level, it's basically we're just telling the algorithm to capture, say, 1,000 degrees of meaning, 1,000 little nuances of the meaning. But what is happening really is so there's a lot of different ways to do it. For example, one of the ways was going to be next Thursday how we capture specifically. But just for now, is basically how many times words appear next to each other. So for example, cat and kitten, they're close together because cat. So the words that cat is used with is similar to the words that kitten is used with. And it's basically the idea that the people that you hang around with kind of define who you are. And the same with words. It's like the words that appear in similar contexts probably have a similar meaning.
It's the word to that thing you're talking about earlier.
Yeah, similar, but that's a predictive model. So that's So it's basically the same concept though. It's word to vec, yeah. And that's the one that I used yesterday. The one that you guys can play around with. But that's in pre-trained, yeah. And you can see how long it took to download. That was only 300 embeddings, right? Yeah. Cool. Yeah. So that's it for linear algebra. The goal of this is to, I guess, mainly build intuition, but also so that you guys can read more into it yourself, because this is so important that, whenever you do anything, you're going to be seeing kind of these terms. So hopefully there's kind of examples and glossary to refer to down the line. Okay. And, what is calculus? It's basically the other half of the equation. So the point is, remember how they're all numbers, right? We talked about how this works. So at the heart of the transformers architecture, what's happening is that you just have a lot of numbers multiplying together, and that somehow predicts the next word. And basically what happens is that all these things multiply together to give you some magical result. But how did these parameters actually improve is what we're going to be diving into today. As in, how did we come about for, all these parameters in the first place? Because they're all going to be random, right? Whenever you have a new word, it could just be completely random. But how do you train the model to have the embeddings, for example, that really represent the nuances of the word? So that's basically the idea for today. Is calculus is all about exploring how those numbers get really, really close to representing our understanding of languages. So this graph is kind of a abstract graph where the x-axis we have the parameter, and on y-axis we have the error. So you can imagine that, for example, if you were to put in 2 as the word embedding, for example, you might get some error. You might put 7 and you get some other error, right? It's just about, so this graph is a really important graph that talks about how well your model performs. So for example, the graph can look something like this, where if you have the values like this, it will have not much error, which is good. But if there's something like here, that's really not good. And calculus is basically what allows us to find the minimum turning point. But it's really easy now, right? Like you can think, everything we've done in methods is just like dy dx equals 0. Oops. And then we just find the best point. But the problem is, this is a 2-dimensional graph, right? Where we have one parameter here. But how many parameters do we have in real life? Like all the word vectors and stuff we're dealing with. Like hundreds and thousands, right? And it's absolutely impossible in real life to be able to find the exact best case. Because for 2D play, it's fine. For 3D, you can visualize. But for 7 dimensions or 10,000 dimensions, it's just impossible for an analytical technique that can find the exact bottom. So this will be more on class things on Thursday of how algorithms can do that. What I'll just say is just a basic introduction of calculus and more so revision, really. So, more traumatic experiences. A slope is defined as a rise over run, which is xt, so we'll say here, over, it will be basically the change in x, delta x, and the change in t, right? So delta, whenever you see in math, just means a change. So what that is the average rate of change between these 2 points. So how can we get the instantaneous rate of change? Let's say we want to find the instantaneous rate of change here. Pretend that we haven't done calculus. We don't know this is a gradient. How will we do it? Yes, you shrink the 2 points, right, to estimate it. So for example, if we make it a bit smaller, okay, so when the 2 points are closer together, you can see that it's starting to better approximate the real gradient. Even smaller is even better approximating the real gradient, right? So it's getting really close now. And then you get to dx over dt. And fun fact, this d actually came from being the lowercase of delta, like the Greek delta. It's like, this is capital, right? So that's a big change. And then we have small changes, it just get represented with a d. So that's why dx dt works. So it's essentially, when we change the time by a little bit, what's changing to our x value? So for example, let's say this is a distance time graph. So this is, say, distance from our home, and when we start counting, we kind of slowly accelerate and drive out of the house. Okay, we get a bit faster, and we slow it until we slow down to a stop, right? So really important way to visualize what a derivative does is that it's basically telling us how much of an impact a small change in time has on the distance. So for example, this is so it's like, with each second, how much further are we traveling? So that's kind of what velocity is, right? So for example, here, the gradient is really low, so dxdt is really low. So it means that when a small amount of time passes, we're not going that much further than before. Whereas here, the gradient is really high. So that means that when we nudge the time by a little bit, there's a huge jump to the grade, to how far we are from home. So this is not really the math perspective that we were taught, but it's really important to think of from a deep learning perspective, because what we're doing is that we want to be nudging our parameters a little bit, and we want to be seeing how much of a jump that has to the overall loss, right? So for example, here the gradient 0 will be no movement. So for example, here is that if you change the time by a little bit, you're not going to be changing how far away you are from the distance. So for example, this is something that can be generalized to like population time graphs as well. So a sharp gradient like this would be referred to, if you change the time by a little bit, there's going to be a huge increase in population. Versus here is not as sensitive to the change in population. So does this kind of make sense in terms of visualizing gradients as a sensitivity of the bottom parameter to the top parameter, right? So what we call this is with respect to. So this is the differentiation of x with respect to t. With respect to just means how much x changes with respect to the movements in t. Okay? So let's go through a couple revision questions. What can be said about the slopes at the intersection? A bit small. Zoom in a little. Okay, is the slope of line 1 greater than the slope of line 2? Yeah, slope of line 1 less than line 2? Yeah, awesome. Okay. Some more revision. This is kind of just a basic calculus, checking that we didn't forget. So what can be said about the curved slope at the red point of graph 1, graph 2, graph 3, and graph 4 respectively? So is the slope of P1 greater than 0? Yeah, right, it's going down, negative. Is the slope of P1 less than 0? Yep. Is the slope of P2 equal to 0?
Yeah.
Slope of P3 is greater than 0?
Yeah.
Actually, this is where it doesn't exist
Where's your 3?
because gradient has to be between 2 points. You can't have you can't find the gradient at when there's nothing on the left. Because you know how there's a difference in rise of a difference in run? There's no difference on the other side. Yeah, this is like discontinuous points, right? So there's no gradient there, so it actually doesn't exist. What about 4?
No.
Yeah, good, because gradients are only applicable when it's smooth. Yeah. Okay, now the reason this is important for our perspective is that you can see that some functions, if it's discontinuous, is really bad from a machine learning perspective because we wouldn't be able to calculate the gradient as easily. So, which of these sentences are true? Is the slope of y1a? Yeah, just mx plus c. Nice. So y1 is that? Obviously not. If a is greater than c, then the slope of y1 is greater than the slope of y2? Yeah. Does it depend on b? No, it just moves up and down. Okay, cool. So we'll go through all the functions in their. So obviously linear relations equations don't need to go through too much, but I just have a note on the bottom about the relevance to us. So it's very simple and used for approximations, but obviously not in real life. The relationships usually are not linear, so it fails to capture the complex relationships, right? Okay, so what's the derivative of this? We'll go around. Is there a microphone? We'll pass this around. You never knew that methods would come up in the 4th year medical school? Okay.
Right, the disclaimer, I haven't done this in 7 years. The first one, the general form.
Yeah.
So the derivative would just be m.
Okay, next person.
Oh, nice. Okay.
You guys are lucky starting off with the easy side?
I think it's half.
Yeah, awesome, right?
The second example already.
Okay. I thought you said what? No, yeah, okay. Yeah, just you drop the term, right? And this makes sense just from intuitive perspective because see how no matter where you are on the x-axis, the slope is still the same, so it's just the slope. Okay. This is a bit more tricky. So this is a rectified linear unit. Rectified just means change in linear, and it outputs 0 for all negative inputs and linear for positive inputs. So basically, you can imagine this is a function that just wipes out whatever is negative coming in and it only retains the positive side. So for example, what is f of 5? What is f of 5? Yeah, 5, because 5 is positive, so it retains that. What is f of 0? Yeah, good. And what about f of negative 10?
0.
Yeah, so this is used, it's called an activation function where it's just, it's like a gate, right? So it only lets in positive values and it kind of wipes out the negative values. Okay, so derivative, next person along.
I think it depends on what x is.
Yeah.
Yeah, so if x is greater than 0, then dx is 1.
Yeah.
And then it's 0 otherwise.
Yeah, great. Technically, there is an undefined point because remember how it's not smooth. But yeah, we don't really worry about that. It's 0 if it's on the right side. And this is the reason why we use it. See how convenient it is to calculate the derivative? It's just 1, right? And you see that a lot of the functions that we have we use that not because it's like the best per se. It's just because it makes computation life so much easier. Okay, getting harder now. Quadratic functions. Okay, so it's really widely used as a loss function. So loss function just means that when the parameter changes, what's happening to the loss, right? How much loss are you expecting? So for this one, okay, what's the derivative of the general form? Yeah, awesome. And then next person, this one? Now using the chain rule. Ooh.
It's not on anymore.
Negative bracket x minus 3 power 1 times 1.
Yeah, which is?
I need to
Yeah, negative x, that's fine. Yeah, pretty simple, eh? So this is like the one thing where I think is really important. Like this is like the one derivative you guys remember. This is the one to remember. Wait, I'll go back to this one really quickly. But in terms of like, how good our graph is, like how this one, for example, how do we measure how good this is, right? We kind of just measure the distance from that to the line, and then we square that because otherwise this will be the same as that. So we just basically square the distance away from the line, and that makes a positive value. So you can imagine that the further away something is, the bigger the square term, right? So we see the quadratic all the time, so it's very important to be able to change all this quadratic equation. Okay. Next question.
Wait, the example or the general?
Do the example.
Okay.
No, it's fine example, but okay.
X squared minus 6x plus 1.
Yeah, just like you drop it down, right? You drop this power down and reduce by 1. But the reason I put this here is that you're going to see this subscript and superscript all the time, and it does look really intimidating at the start. But then all this means is that, okay, it starts at 0 on this side, okay, that's just constant term, and it starts at n on that side. So there's n number of terms, and each term, can you see how an and an minus 1 is different, right? It's just like what all a is it's just a placeholder, and this happens to be the nth a, and this happens to be n minus 1a. And the reason we don't do like ax n plus bx next is just we're going to run out of letters. So it's literally the same as like a, b, c, d, e. It's just that we need to have infinite placeholders available. Okay. Derivative of this form?
That was
Next, yeah,
Oh, yeah.
pass it on.
Wait, what's going on? I have to just give that.
Yeah, this one. Derivative of this.
6x squared minus 6x plus 1.
Yeah, awesome. Okay, pretty simple as well. Exponential function. So this is really important to model the rapid change of decay of variables, and it's used because it's so easy to derive it. So what's the derivation of this?
E to the S.
Yeah. So again, it keeps life a lot easier, right? It just derives back to itself. These are very important properties. Just a quick revision.
But what's optimization? Like, is it you strictly an optimization?
Oh, optimization just so optimization. Okay, what optimization is like basically finding the minimum turning points. So like when you find the station, the local minimum, that's basically what we're trying to find. And the reason this is helpful is because you need to use the derivative to get like dy dx equals 0, right? It's just a lot easier when there's an e of x there because it doesn't complicate the equation anymore. So all optimization refers to is basically like using calculus to find the best.
So you're saying like literally like computation?
Yeah, computation easy, exactly. So we're going to see some more computationally simple functions in a second. But yeah, very, very nice. Important properties. Okay. Log as well. So this is the inverse of exponential. Who are we up to? Okay, what's this? It's one of the hardest one to remember. It's just 1 over x. And again, computationally very simple. Yeah. So this is really computationally helpful when we're multiplying probabilities, because it's really good at modeling diminishing returns. Because imagine that when something's really close to 0, right? In normal, if you just multiply it normally, it just gets infinitely smaller. If you multiply 0.1, 0.1 or something, just multiply a lot of that, it will get really, really small. But notice how the log, it dips all the way down. So even when things get really close to 0, it's still quite separate. That's why it's really helpful one that we do. Another important property, when you add two logs together, it's the same as the inside thing multiplying. Okay, so quick revision of yesterday's summation and product notation. Is this equal? Okay, so hands up for is equal. Hands up for not equal? Yeah, awesome. So the left-hand side is basically log 1 plus log 2 plus log 3, right? Remember how this is a counter, and this is how much we go up to. So 1 plus 2 plus 3 plus 4 plus 5. That's equal to the log of 120. But the product will be log 1 times log 2 times log 3. So there's no way we can simplify this further, right? When we add them, we can combine the inside term. And again, it's very, very helpful because normally products are pain to deal with calculus-wise. Do you guys remember the product rule? UV is equal U dash V times UV times U dash. Yeah. Yes, exactly. So, but with log, everything's added up. It's very convenient, right? So that's why we prefer to work with logs. Okay. So that's just revision. Now the new stuff is here. It's about vector functions. So these are scalar functions because they take in the input is a scalar, and the output also happens to be scalar. So that's all the functions that basically we've been dealing with up to this point, right? So these are the equivalent vector functions. What's the difference? Yeah, so remember when I say all bolded means it's a vector? And again, I know that the I, like the subscript, kind of is a pain, but by default, the bolded X refers to the vector. And then let's say the vector, each individual index in that vector just happens to be represented by I. So for example, the first one will be like x1 and x2, x3, so forth, okay? So what it's trying to say is that for every xi belongs to x. So remember how this means within? So for every single value within this vector, what we return is the value itself, if that value happens to be greater than 0, or 0 if the value happens to be less than 0, right? So all this is that it's essentially just putting every single term through this check. So for example, if a vector has 1, 2, 3, 4, it will just go 1, 2, 3, 4 back, right? But if it's like 1, 2, negative 3, 4, it will return 1, 2, 0, 4. So it just checks that every value is positive before it gives you the vector back. Same with all this. So notice how what this does is that it takes a vector as an input, and then it gives you a vector back, right? So let's say they're objective functions. So this is another type of term you'll see a lot, objective functions. A loss function is basically how bad your model is. So you want to minimize the loss function. But sometimes objective functions, you want to increase that. So this could be the score of a game, right? So this is optimization. All it is trying to look for the maximum or the minimum. So let's say that this is the objective function, the quadratic equation. So we want to find the value of x that maximizes this function, right? So how well does x equals to 1 do if we put it in? So what's 1 subbed in? Next person? Not out of the woods yet. Okay, that's true. Nice. But yeah, it's just 3. So we just sub that in and then we see how that is, right? What about x equals to 2? Or 3. So essentially, every single time we run something through the loss function, we don't want to ever put in one thing. We always want to put in like a ton of things at once, because imagine we're training like 100 words, right? 100 word embeddings to see how well it does, rather than putting every single word through the function at the same time. Wouldn't it be better to do it through parallel computing? Like just give it to you all back at once, right? So that's basically the idea of these functions. So we can put a lot more values in at once and it returns us everything back. So again, notice how the only difference, right, is that the x is now bolded. So what is f of 1, 2, 3? So this looks a bit weird because what we're doing is that we're just replacing the bold x with the vector 1, 2, 3. So what's 1, 2, 3 subtracted by 3? Remember the numpy operations? So what's the new vector inside the bracket? Pass it along. Yeah, that's it. So remember how numpy is kind of negative, is all this is that every single element gets kind of broadcasted inside, right? So it's -2, -1, 0. Okay, what is that squared now?
410.
Yeah, 410, right? And then multiply, scalar multiplication.
-2, -half.
Yeah, nice. And then +5, okay? So same thing. So all this is trying to do is that it's literally the exact same thing. And just visualize that as though we're putting in multiple things at the same time. So this is why NumPy arrays are really powerful again, because if you put lists into a function, that doesn't work. So this is more mathematical notation, but this is something from methods as well, right? Like f of r to r is equal to f of x. But we're actually dealing with high dimensions now. So the input domain is a R3. So R3 means a vector of 3 dimensions. And getting R3 back just means that we're outputting a vector of 3 dimensions. So this is kind of putting them side to side. Right, this one's the same as the other one, except it just has a bolded x. And when you put it in, you get vector length 3, you get a vector length 3 back. So if you were to put in a vector length 7, you can get a length of 7 back. So more formally, it is basically it's a function that takes Rn and gives you Rn back. And remember, n doesn't mean anything. N is always just a placeholder for basically how long something is. So we try to get comfortable with these math notations. Oh, okay. So some other functions we already seen that takes in a vector and then returns a scalar. Any ideas of what that is? What's a function that can take in vectors and return a scalar?
The norm.
Yeah, the norm, right? Or even the dot product, but that takes in 2 vectors as input and returns a scalar. So we've all played around with the dot already and the norm. So it's very, it looks a lot more tricky on paper than it is in real life. So quick revision again. So starting at 1, the first term of this, we're squaring the first term, and we're squaring ISO 2, the second term, and we're squaring the third term, all the way to the nth term. And then we're getting the output, putting that all through a square root. So this is again where it's really important to keep track of dimensions, right? So this when we get the result, this summation notation back, is it a vector or is it a scalar at that point? Yeah, scalar, right? Because we're already essentially taking every element from that vector and then combining them together and then making it square rooted. So that's that. And when we have remember how is a length n becomes a scalar, right? So a dot product is actually looks a bit more complex. It's like Rn times Rn to R, because it's taking 2 vectors as input. So this is less necessary, just so you see it and know what it is. Domain is a type of input the function expects, and then codomain is the type of outputs to return. Okay, let's write some down. Oh, okay, so this is a demonstration of what it looks like in Python. This is that function, right? And notice how I'm not telling Python that it's a NumPy, like it's a vector function. See this objective x. If I was to put in the 1, for example, it's just the 1 that we calculated, which is returns a 3. But if I was to put in NumPy array 1, 2, 3, it's just going to get the same thing back. So Python's very clever in that way. No need to define a domain codomain, it will just automatically treat it. So that's why, again, it's probably more NumPy being helpful than Python. But yeah, let's have a go writing a sigmoid function in Python. I think I have the notebook, but I forgot to link it, so I'll pause screen sharing for a second. Cool, so this is kind of how we'll do it. So most people figure that NumPy has an exponential function, which is really nice. I think it does have e as well. You can search out somewhere, or you might need to import math. But this is the best way to do it, numpy.exp to the power of -z. And just as a quick demonstration as well of how you should be labeling your functions. So I know that, like right now it's an exercise. So I don't expect you guys to write it as if someone else is reading it. But this is a gold standard common style. So you start with what the function is trying to do, which is to compute a sigmoid of z. You tell them what parameters is going to be in there. So in this case, it's z. And you also tell them the type of input that it can expect, right? Scalar, NumPy array. Not this, actually. That's my bad. So these are the input values. And then it returns scalar numpy array. So this is a form of the return, and it's a sigma of the output. And the reason this is really important is because it's actually not just helpful for anyone reading your code later on, but just like when you're doing it, when you be able to write a function, it's really nice to type out your thoughts out loud and clearly define what your function can accept and can't accept. So the ReLU function, has everyone managed to do this as well? So do you want to pass the mic along? Yeah. How did you do that? Have you done the ReLU function already? Okay, yeah. We'll maybe have a couple seconds to do the ReLU function. Actually, we'll just do it now. How would you do it if you were to write it now? What's your plan?
If x is greater than 0, then return x.
Yeah, literally, just if x greater than 0, return x, else you return the 0, right? Awesome. Oh, by the way, if you guys are done quick, try to play with matplotlib to see how you can plot this using Python as well. But yeah, this one's pretty simple. Again, using the Gaussian notation, it computes a rectified linear unit. And this is really helpful because a lot of your functions might be tended to have an acronym. And I think maybe not for all the clinical years, we all know like at the start how painful it is reading everyone else's acronym, right? So be nice to other people and define your acronyms if you're going to use them in your function, the type of inputs it expects, and then the output. So I've used a function called np.max. Basically, this is how you might see the rectified linear unit written in real life. Is max 0x. What that means is that you're giving NumPy two options. It's 0 or x. It's just choosing a bigger value. So for example, if you put in a 2, okay, is it 0 or 2? Which one's bigger? 2 is bigger, so it gives you the 2 back. But if you put 0 and -1, well, that means that NumPy will be, okay, 0 is bigger than -1, so I'm going to put 0. So basically, this is trying to say that it will give you your value back if it's x, if it's bigger than 0. But anything else, it will just give you the 0, Okay. The ton function. So the first part is to do the ton function normally, like using the formula. And second tries to do it, oh, this is not the graph of the ton function, by the way. It looks a lot more like this sigmoid. And the second way is to try to do it without NumPy, yeah. And then try to do it with NumPy as well. How many levels of abstraction you can have. Now, this is kind of, there's actually no point writing this function because NumPy does it for us. So your function returns an np.tonH. So you might as well just do np.tonH in the first place rather than your function called tonH, right? But yeah, just for the sake of argument, this is a hyperbolic tangent function of x. The parameters are scalar and arrays, and it returns a ton of the output. Quick note, these are called squishification functions. So notice so what does it map what to? So what is the input that gets accepted by the sigma function, for example? What values can be applied? Any real number, right? So any real number, it will have something to be mapped to. But what about the output? What is the range of this function? Yeah, so basically, intuitively, you can visualize this as almost a probability that you're getting, right? Because you're getting a 0 to 1. So when they say activation function wise, it's almost like a probability of like how of a neuron firing, for example, or how much of a neuron, what percentage of a neuron fires. So this is a really helpful function to kind of restrict the range of things you can have. So you don't, if you have something like negative 10,000, for example, right? Like that's ridiculous. It just goes back to 0, or if you have a lot, it just restricts it between 0 and 1. Whereas the rectified linear unit, this is a lot less conservative, I guess, in managing like exploding values, for example, because if you have a really high output, it can just be super, super high. But at least it stops you from having a really negative input, a really negative output. Okay. This is how you do it manually, I suppose. But basically, it's just spot math, right? Where the numerator np.exvpx minus np.exp, okay, over np.exp plus fxp. So it's exactly this, but just worded out manually. So in terms of doing it without a library, you can just define e to like 16 decimal places. I'm sure you can copy that from somewhere, and then define that within the function. It's really good how to define that within the function so that nowhere else ever needs to use your constant e, for example. And then you can just do the 2 star sign to denote exponentials. Okay.
When you're writing like functions like that,
Yeah.
is there a convention in terms of when to put spaces and when not?
Oh yeah, really good question. So generally around the brackets, you don't want to have spaces, but it's really nice to have spaces between this, because the coding typeset is actually every single character is the same amount of width. So that's how everything lines up so well. So look at this. So def, you see how it lines up with 4. That's usually I think Python is, I'm not sure if it's 2 or 4. I think it's 4. That's what most people do. But then for Colab, you can see it's actually 2 spaces, which is annoying. I always change it to 4. But yeah, the convention is that you put some space around the operation marks. That's really, yeah. And brackets around everything. Like more brackets is always better. So we can actually take derivatives of scalar functions, obviously, but we can actually take them off vector functions as well. So for example, the derivative of a normal function is denoted with this dash, right? So f of x is equal to that. Derivative will just be f dash. This is called the grad function, grad for vector functions. So notice how the first thing is the same thing, but with a bolded x to denote the vector. And the bottom is just the same function, but rather than having a dash, we denote it with an upside down triangle. It's called the grad function. So basically, grad for gradient is representative of the gradient of your function, right? That's what the derivative is trying to compute. So it's the exact same thing. For example, all these functions earlier, they will all have their own corresponding grad function. So literally the exact same thing. Like this one will be like just with a upside down triangle to denote that it's a grad function, and then you do it as you would normally. Okay, but yeah, this is that's basically it for that. So now the thing we're gonna finish on is just something about the chain rule. And I'm not really gonna there's no point ever talking about I'm not gonna make you guys do 10 exercises on computing different chain rules, right? But the point is more to get intuitive understanding of what the chain rule is trying to do. So remember how way earlier I was saying that what the gradient is about sensitivity. So a high gradient just means that if you have a small change in time, that's gonna have a huge jump in terms of how far away you're gonna go, right? So small change in t refers to a big change in x. Now, from the perspective of chain rule, it allows us to multiply. Oh, where can I go? Okay, basically, it allows us to compare the rates and relate them together. So, for example, let's say you're trying to drive up to the top of a mountain, and you're trying to drive up this, right? So your time, when time goes, you're gonna go higher up. You're gonna be higher as soon as you go the further, the longer it takes. But then it's colder towards the top of the mountain compared to the bottom. So these are the variables: T for temperature, capital H for lowercase, I guess H for height, and T for time. So what is dt over dh put into words? Then pass the mic along. Where is it? Oh. That should start. Yeah. So what is dt over dh here? Yeah, okay, so it's actually the difference in temperature over the change in height. So what this means is that when your height is going up, how is it affecting your temperature? Does that make sense? So the bottom thing is what we change, and the top thing is what we try to have the effect of. So for example, would this be positive or negative? Don't pass it along. Thomas, you're back. So do we expect dt over dh to be positive or negative?
So it'll get colder as you go up.
Yeah.
So as h goes up, t will go down.
So it's negative, right? Awesome, great. So that's what it means. So when we have a small change in H, what is the impact of this onto the temperature? Okay. Now, well, dH over dt.
The same thing, but with respect to the height changing over time.
Yeah. So would you expect this to be positive or negative?
I think positive then maybe.
Okay, so if you go down the mountain, is that what you meant? Okay, sure. Fair enough. Yeah. So to keep it simple, we're only going up to the mountain. But yeah, dH. So at least on the way up, it will be positive, right? So when you go slightly, say 1 second longer, you're going to go slightly higher as far as your car goes, right? So basically, what this does is it captures the ratio of the time and its effect on H. So now what we're interested in. So this is what is written out. So temperature changes with respect to height. So with respect to just means when you change the height, how does that change the temperature? And when you say height with respect to time, it's just when you change the time, how is that changing the height? Where will dt over d capital T over dt pass it along?
So that's how temperature changes with time.
Yeah. So would you expect this to be positive or negative?
That'd be a negative rating,
Yeah, negative, right? So, but the problem is we can't get this straight away, right? So we don't know. Obviously, when time passes normally, you don't just suddenly get colder. So how we compute dt over dt is that we can't. There's no intuitive sense to make to grab it normally. How this works is that we have to compute it in relation to how temperature changes with the height, how temperature changes with how height changes with the time. So that's what the change rule does fundamentally, right? So what this is that temperature changes with respect to time. So what we know is that when we go higher, how much temperature falls. Okay. We also know that when we go further along the time axis, our height will be increasing. But we had to relate these together in order to figure out how the temperature changes with respect to time. So how can we put it together? So what is dt over dt in terms of the two things that we already know? Pass it along.
Multiply them together.
Yeah. So multiply together. This is what the change rule is, right? And so math teacher's gonna hate me for saying this, but it's kind of like you're cancelling out the dh. This is obviously not the case because dt over dh this is one symbol on its own, right? It's not a fraction. It just visualizes a fraction because it's really everyone thinks of it this way, and that's okay. But yeah, so that's what dt dh and dh dt is. Okay, so it cancels out. Okay, so basically this is the idea of the change rule. We want to figure out the effect of time on the temperature, but that depends on the height, right? So that's why we have a little intermediary, which is we need to figure out how our time affects how high up we go, and how high up we go affects the overall temperature. This is a formula. Just for one quick exercise, try to use this and compute the derivative of the sigmoid function, which is this. And for bonus marks, derive this, like find the derivative of the tan function. This is the only. So you guys, it's two ways to do it. If you guys really don't remember your math or like it, you can do this. Try to search up. There's something called SymPy, Symbolic Python. They have things to help you do it. Other option is to do it mathematically. So it's good old pen and paper. And just like this is like 1 plus e to the power of negative x to the power of negative 1. So you can do a chain rule like that. Okay, go. Pen and paper? Who's on a pen and paper game? Pen and paper game? Alright, awesome. This behind everything we've talked about. So this is written by Kirk Baker. Yeah, it's very nice introduction of vectors, and it's like a good summary sheet you can remember and refer to. And hopefully this is what I mean by a lot of math is written in like this kind of weird ways with the fancy notation. So hopefully you guys are a bit more comfortable with reading that now. But the point of this was actually to show how painful PCA is, like to do by hand, and because like you don't have to do it. So this is that. Single value decomposition is kind of the algorithm powering PCA. So I'll just keep scrolling and like this is a full example of singular value decomposition.
Or something.
Huh? Oh no. Alright, go for it. Okay, so here it is. Singular value decomposition. This is a algorithm powering PCA. And like honestly, this is so bad. Like, I like my math and I haven't even bothered to work through this mathematically. But yeah, you guys feel free to explore for the sake of academic curiosity. That's that should be your drive. But yeah, look at it's a lot of work. This is like, and I'm not even that far down. It's more. There we go. So that's another example, but yeah, it is very painful to do it normally. So that's why it's really important to be on the side of intuition rather than getting bogged down by that. So in terms of does anyone want to come up and compute the sigmoid function, like the derivative? So has anyone managed to do it with SymPy or like with Python? Anyone? CJ, did you do it? No? Okay. But yeah, so you can do it with some Python libraries, but we're going to be doing Torch next week, which is basically does it all for you. So as far as sigmoid function derivatives go, it's not the most educational perhaps, but the reason that I want to bring it up is because the end result, so after you do it, it should actually be the sigmoid function's derivative is equal to the sigmoid function by itself times 1 minus the sigmoid function. So most of the people have got to this step who try, but there's actually, you can simplify even further to get to this step, and I'll leave that as a challenge. But basically, see how convenient it is, right? It differentiates. It's almost like E, where it's just itself, but this is just that or 1 minus that. So it's very convenient to do for the derivative, which is again why we use it in the optimization problems. Okay, so that's basically it for this morning. We're going to keep it light, and just a reminder that so in the afternoon there will be Brian on probability crash course. But just a reminder that tomorrow will be basically a full coding day, and it's really important to at least get through be able to get through the Kaggle Python course by itself, if you guys haven't already, because otherwise the coding will just keep ramping up. But if you guys do the Python Kaggle exercises and the tutorials, it should be, you should be able to do the tomorrow's problems quite comfortably. Not comfortably, but at least be in a good starting position. Okay, cool.